Okay, now we are back into looking at how we use the sampling distributions. So, as you see on your slide, we have P x, which is the probability distribution, and then capital P x is the cumulative part of that. So, these are the curves that go together. So, if you look at n such values are chosen, such as resulting value plotted as a histogram will have the same shape as the Maxwell-Boltzmann distribution. So, those are the random sampling values we are interested in, and those are n such sampling thing. So, if I look at this chi I, which is a variable which represent random numbers, and I can have n c such numbers which we are looking at. So, if I look at the probability P x I will becomes E I. So, this is what we are looking here, that the random number generator, if it is between 0 and 1, and x I, which is the probability of finding a particle at position x, they will become same. So, I can now apply the Maxwell-Boltzmann distribution, and knowing the shape which is exponential minus beta u, we are now able to sample that space which belongs to the Boltzmann distribution function. So, with that understanding, now we are able to take all those distributions of the positions collected from the Maxwell-Boltzmann distribution, and then create the average property calculation. So, we go back again and take resort to our familiar machine, which is statistical mechanics. So, now if you look at here, the property of any variable a, you can look at for 3n dimensional space. So, this is where 3n dimensional differential of that particular property with respect to r, which is the position vector, and then over all particles. So, we are looking at, and it is with the e to the power minus beta u or n. So, we are looking at the Maxwell distribution of the position vectors and the overall position vectors, which is where the bottom, if you look at the denominator, is what we call as partition function, which we are familiar with. We looked at that earlier when we talked about statistical mechanics. So, for a property a which belongs to certain amount of velocity distribution or that particular variable distribution, now we are able to use that in the sample which has the bias of Boltzmann distribution. So, it's random, but it is not completely random, because it does have a bias of Maxwell Boltzmann distribution factor. So, exponential of minus beta u is that Boltzmann factor, which essentially is looking at this distribution function, and minus u is potential energy, Kb is the Boltzmann constant, and T is the temperature. With that understanding, now we can use our formulation purely from the perspective of what we call is the position vector of the particles, where now we can choose n c such configuration randomly and integrate and use a normalizing function of partition function over all particles, and that is where we can get the average property calculation purely based on the configuration variables. And what happens in this case, we can do all these calculation and go to millions of these such configurations, and so in some cases the u may become greater than kBt, and as you know, kBt is in the denominator. So, if you have a very large kBt, then the potential energy divided by a large number in exponential function will become close to 0. So, some of them are really not useful. So, essentially we need to now be very clever in terms of choosing the moves that are meaningful, and that is where Metropolis algorithm came to being, where we are going to do importance. We look at what moves are important, what are not important, throw them out, and that is where we say importance sampling. So, if you look at here, in this case, if we choose the configuration not randomly, but those belong to the Boltzmann distribution and weigh them equally, 1 over n c number of particles, and say that their weight is equal, then we have an importance sampling with only those configuration that belong to Boltzmann distribution function. So, if you look at the position vector r n, and we are looking at configuration sample from the distribution of exponential minus beta u, which is and beta is 1 over kBt. Now, we have importance sampling that is established. So, now what did Metropolis do? Metropolis said is that I am going to now take a 2-dimensional space of x and y, and I am going to move x and y both, and then I am going to calculate the trajectories and see not the trajectory, but the configurations, and see which configurations I should look at, which should I keep and which I should not keep. So, he came up with the criteria for that importance sampling, and that was his major contribution why it is called Metropolis Monte Carlo, because it was an energy criteria which allowed you to sample the energy space. And the important, and as we look at here, so now let us look at that formulation. Let us see, we have particle x and y, potential energy u, which depends on the particle position. Now, imagine displacing particle from its initial position to a new trial position, x plus alpha psi I, and as you know, this is psi I is the random number generator between 0 and 1. So, we are again taking x and y and adding some new terms to it, so that we have a new position. Alpha is the constant to be adjusted, and if you look at psi is equal to 2 psi minus 1, I is equal to 1 or 2, notice that the psi value will go between minus 1 and 1. So, between this minus 1 and 1, we have all these random positions coming through, and now we are going to use the algorithm in a very simple algorithm that you can program in few minutes and start your own Metropolis Monte Carlo method. Here is that you are looking at MOOC system in a way that just described, in the sense that it has positive values added to the x and y situation, and the random numbers are generated between minus 1 to 0 to 1, positive 1. So, if you look at delta u for final minus initial. So, between the two different samples or configuration, if we calculate the energy for the one which was initial, and then the next one which we are looking at, and so we find the difference of the energy. So, now we are looking at the energy gain from the move. So, if the energy gain is less than 0, then accept the move. This means means leaving particle in its new position. So, what it is saying is that if the energy change is less than 0, then you are essentially leaving the particle where it is, and if it is delta u is greater than 0, then still accept the move, provided E minus beta delta u is greater than the random number generator value. And if you look at the psi is the third random number generator in the present sequence of between 1, 2, 3 and 4. So, if you look at every time you generate the random number generator, now you have a criteria, because that random number generator is giving a new position. So, you are accepting or rejecting that configuration. So, if it is less than 0, and so you can either leave the same position, so no change in the position, or you accept it as the energy goes up. So, essentially what it does the energy going up the hill. So, what it is doing is that although it is going towards the bottom of the energy or minimization, but it is also allowing energy to move up the hill. So, that if you were caught in a local minima, it is going to move out of it, jump out of it, and find the what we call as the global minima. The whole idea about sampling this surface of potential energy, it is almost like hills and valleys. So, you may be stuck in a hill in a small ridge, but you want to find the global minima which is way down there. So, this kind of simulation, it allows you to go up the hill and also collect only those configuration which follow the distribution e to the power minus beta delta u, where the delta u is the change in potential energy. So, this allows now me to calculate Metropolis Monte Carlo method. This is what is the famous Metropolis MC method. What it allows me to do, number one, no need to calculate equation of motion. So, I save lot of computation time, although I did not save time in terms of calculation of potential energy, but that is the criteria for me to accept a particular configuration. In MD ensemble, averages are sampled by the random particle configuration that follow Boltzmann distribution that follow metropolis algorithm. So, in this case we are talking about MC algorithm, not the MD. So, in case of MC ensembles, this is what the criteria is, and under certain equilibrium conditions MD and MC both can be good simulation method, and they may give the same results even with less computational time in Monte Carlo. So, that is a very good phenomena for certain situation. And if you look at the time dependent dynamical properties are hard to predict, although you can use kinetic Monte Carlo simulation as well, which we will touch upon. But in this case that information is kind of lost, because we are not looking at the trajectory, how they move through the phase space is not there, and because of that, and because we are not looking at trajectory but just the equilibrium configurations, MC is more general than MD for range of complex situation that you can apply, because range of complex situation may not be allowed in MD, because you have to have proper ensemble, proper dynamics, Hamiltonian or Lagrangian dynamics, but in case of MC does not care. MC wants to know within given boundary conditions, which are still applicable, what are the equilibrium configuration following the Boltzmann distribution function. So, this is a what we, that is why we call it smart sampling. It is a smart way of looking at configuration. So, let me stop here and let me then give you some examples and what are the features as well as what are the advantages and pros and cons of using Monte Carlo simulation, which we use quite often in conjunction with molecular dynamics simulations. Thank you.